All right, welcome back to another episode of Connie 352. Today we're going to be discussing heating systems. Yesterday I posted some videos for you to watch, not of me, but a couple pretty good ones on steam systems. Some of them were fun. They were Mythbusters. Some of them were serious. They were about like the New York City steam system. If you haven't watched those, please go back and pause this and watch those. They're not very long, but they're pretty informative and give you a little bit of a good background as we get into heating systems. All right, so do that if you haven't yet. Like I said, they're not very long, but I think they're pretty interesting. Okay, let's get started talking about heating system basics. We're going to spend more time on air conditioning than we do on heating. Personally, I think air conditioning is the more difficult topic, and air conditioning, when we get into commercial buildings, usually it's air conditioning that dominates in terms of energy cost and dominates equipment sizing, ductwork sizing, and that type of stuff. Heating systems are very important, though. So I do want to discuss those. We're going to do those first, and then we're going to talk more about air conditioning probably next week. All right, let's take a look. Let's just start with something relatable, something simple, just like a residential grade furnace. A furnace, and let's talk about options that we have for heating. What kind of different fuels could we use for heating a residence? Because they're going to be the same options that we use for heating a large commercial building. Essentially, they're all the same. In other words, we're going to use either a fossil fuel that we set on fire, or we're going to use electricity, which is sent to the building via transmission lines, but most electricity is generated by fossil fuels set on fire, right? Coal, natural gas, that type of thing. The difference is really just, it's all about transmission and transmission loss. It is more efficient to take the fossil fuel and burn it locally than it is to use that fossil fuel to generate electricity and then go through all the losses in electricity, the transmission losses and the generation losses, and then send it to a building. All right, but you'll find different locations will use different sources and for different reasons. And we're going to get into some of those reasons. So let's just look at some of our choices for fuels. The most common ones: natural gas, LP, propane, and some type of an oil like a fuel oil. Natural gas is by far the most common. If you're in an urban environment, they probably have natural gas piped to you in the street. And it's fairly cheap. It's readily available. It burns pretty cleanly. All right. There's a lot of advantages for natural gas. Some of the disadvantages, though, is that if something happens to the supply of natural gas, you're kind of in trouble. In other words, you don't have a storage tank of natural gas on site. It's always going through the pipes, and if something happens to that disruption, you're in trouble. Obviously, just look at what happened here with electricity in our distribution system in Iowa with the hurricane just before classes started. So distribution systems can be disrupted. If you have LP, and most of the time you're going to see LP in a tank in a rural setting. It is slightly more expensive than natural gas. It is also slightly more dangerous in terms of the possibilities for leaks and explosion than natural gas. Almost every year in the state of Iowa, a couple residences will blow up in the country because of LP leaks. LP leaks. And the thing about LP propane gas is that it is heavier than air. So if there was a leak, say at someone's furnace, a leak in the pipe, a leak in the heat exchanger, that unused potential energy gas is going to sink to the bottom and fill the basement up from the bottom up. And then it'll keep going until it finds some type of a spark, and then it can explode. So LP is dangerous. Having a big tank of it on site is dangerous. What if somebody drives into it or runs into it or lightning strikes it, or who knows? Now, those are all kind of things that don't happen very often, but it is possible. However, if a catastrophe happens, the nice part about having the tank is that you already have it. It is physically at your location. Kind of like oil or fuel oil. Fuel oil is really, really similar in properties to diesel fuel. In Iowa, a lot of, before LP tanks were common, a lot of farmsteads had fuel oil because the same people that delivered diesel fuel to the tractor would also deliver fuel oil. It was very convenient that way. Farmers understood it. It was easy to manage. You have a tank, you fill up the tank. It's that easy. For businesses that need to have heating as a critical item, like a hospital, many times they will have boilers that burn both fuels, maybe natural gas and LP, or natural gas and fuel oil, because they're willing to store some of this fuel on site, at least a couple days worth, just in case of an emergency. Think like earthquake, hurricane, that type of setting. And while a business is like, okay, if there's that bad of a catastrophe, we're not going to be open anyway. A hospital is a different story. If it's a bad catastrophe, we need to be operating. And in northern climates like Iowa, heating can be a life and death type of a thing. So fuel oil, you're not going to see a whole lot of in residents here in Iowa, but in the Northeast, say from New York City and north, you'll still find a whole bunch of residences that burn fuel oil, and they have a local, tank on site. All right, let's talk about efficiency. Think of, as we're talking about a boiler or a furnace, most of the time we're going to list this efficiency as a percentage. Think of this AFUE or thermal efficiency as natural gas and fuel oil and LP per gallon, per cubic foot, whatever it is. They have a certain amount of potential energy. There's a number of BTUs there that are in that fuel. We're going to set them on fire in a controlled way in a furnace. Most of that heat is going to get transferred to the room, the space. Some of it, though, will go out the stack. We can't have a heat exchanger that is 100% efficient. And here, caveat to that, a heat exchanger where we're burning a fuel. In other words, there is excess junk that we don't want in the house. If we're burning a natural gas or a fuel oil, it produces all sorts of harmful gases, carbon monoxide. It'll also produce the various, N2, S2, the sulfurs, nitrogens. Those are all things that we do not want to breathe. They are deadly. So that part needs to be exhausted through the exhaust stack. But as we exhaust that to the outside, that will still have some thermal energy in it. In other words, we can't get all that energy out of it. How good of a job a furnace does is determined by the efficiency of the heat exchanger and expressed as a percentage. 70%, 80%, 90%, those are just some examples. If you bought a house with a very old furnace, it might have an efficiency of 70%. I don't know if any of you grew up with an older furnace that had a standing pilot light. In other words, just a little bitty light by the heat exchanger that actually set the gas on fire. That is only going to be about 70% efficient. Any modern furnace is going to start at 80% efficient, and it'll have an electronic igniter and not a standing pilot light. But we can do a lot better than that, actually. We can get up to upper 80s, even the low 90s in terms of efficiency. You might buy a new Lennox Pulse furnace that is 94% efficient. Something important to understand, once we reach 88% efficiency, it's not on the slide, but write that down. 88% efficient and above will cause condensing in the furnace. Now, condensing. Let's look at this. Let's unpack this term for a second. Condensing is when we take that natural gas and we set it on fire and we put it through a heat exchanger. The exhaust stuff that we're getting rid of, remember I said that was the dangerous stuff. That was the carbon monoxide and other products. That exhaust stuff that we exhaust not only has carbon, sulfur, nitrogen, but it also has water in it. Water is a byproduct of burning natural gas. Water is a byproduct of burning gasoline or diesel fuel. You'll see in the winter, you'll see a car tailpipe dripping. That water didn't come from the surrounding air. It came from the combustion of the fuel in the engine as it is exhausted out the tailpipe. However, in winter, that tailpipe is very cold. You'll see it sit there and drip because that water condenses. In other words, it gets cool enough that it forms a droplet and drops out of solution. It condenses and drips out the tailpipe. Well, think of the same thing happening in a natural gas furnace. I set that fuel on fire. I transfer as much energy as possible into the people space, but the leftover combustion products I exhaust out the stack. If I'm doing a good enough job of that, if I've got a high efficiency furnace, that water is going to condense in the stack. And then I've got to get rid of that. In other words, I've got to have a condensate line off the furnace. If you go to like a residential furnace, you'll see a condensate line coming from the air conditioning coil, but you'll also see one coming from the furnace section. That is condensate that comes from the burning of natural gas. Something to be cautious of, though. That condensate is going to cause acids to form. When that water drops out of solution, it combines with the carbon, the sulfur, the nitrogen, and makes carbonic acid, sulfuric acid, nitric acid. So that condensate that comes off your furnace is very, very acidic, which means if we have a high efficiency furnace, we'd better have stainless steel heat exchanger parts and stainless steel, or at least non-corrosive, exhaust stacks. All right, so let's come back to those exhaust stacks in just a second. Let's go to the basic parts of a furnace. All right, high efficiency, low efficiency, they all have the same parts. We have a cabinet, we have fans, we have a heat exchanger, we have a combustion system. Combustion system, where I take that natural gas, I combine it with some air so that I can set it on fire, and I have igniter. The air conditioning coils we're going to talk about later. Usually air conditioning coils are an add-on. We're going to bolt those to the top of the furnace. We're going to have controls. Controls are simply, I've got a thermostat. I've got an off-on control. When do I need to turn on the heat? When do I need to turn it off? Venting. If I'm burning a natural gas or I'm burning a fuel oil, how do I get that exhaust junk out? That's the vent system. And then filters. Filters on the return air that is coming back from the space. Here, I got a schematic of it on this next one. This is just a schematic. I'll have some better diagrams here in a second. But return air comes from the room, from the house. We have a fan on the furnace that blows it through a heat exchanger. Now, before it hits the fan, we have a simple residential quality filter that filters that return air. I don't want dust, hair, lint, whatever it is from the people space getting on the heat exchanger. I'm going to blow the air through the heat exchanger. All right, the space air goes through the heat exchanger this way. I'll have a separate burner section that pulls in combustion air, maybe from the mechanical room, maybe from outside. Usually the high efficiency ones take air from the outside. I'll put it through a burner, set it on fire, and put it through a heat exchanger. Important thing about the heat exchanger is these two air streams do not touch. They are separated by the metal wall of the heat exchanger. I want the combustion products that are hot to exchange energy with the return air, but I do not want those two airstreams to mix. If there is a failure of the heat exchanger, like a crack in the heat exchanger, that is a very, very major failure, because now the deadly carbon monoxide can get into the people space. That is why if you have a natural gas furnace, you also need a carbon monoxide detector. So anyway, the exhaust stuff goes up the exhaust flue and outside. The now warm supply air goes back to the room. Let's take a look at this simple little illustration. Cool return air comes back from the room, right? Goes through the fan. The bottom part here is the fan. There's a filter on the side of the furnace. We blow it through this heat exchanger, and now it gets hot. Have a little close-up of the heat exchanger on the next slide. All right, but this other fan here, this is a combustion air fan. Remember, those two air streams don't cross, so we need two separate fans. That takes this, and you'll see it just kind of head out the back here. All right, now, the part on top, that is for a later discussion. It's hot now, but this is the air conditioner, the air conditioning coil that we're going to look at when we talk about air conditioning. Think of this coil as like an accessory that you bolt on to the furnace section. All we're going to do is we're going to use the same ductwork and supply fan for the air conditioner that we do for the heater. All right, and then once this air is hot, we blow it through the ductwork into the room, and the process keeps on going. Let's take a little, this is a picture of a real one, right? Here's the return air coming in the bottom. This is just a big metal cabinet so that you can't see all the internal parts. The return air comes in here, goes through a filter, we put it through the heat exchanger, and then the silver ductwork on top goes there, goes back to the room. See these PVC pipes that are coming off the top? PVC, one of them is combustion air coming in, and one of them is exhaust products, the vent going out, the junk we want to get rid of. This is a high efficiency furnace, and the reason we know this is that they are using PVC pipes. If this was a lower efficiency furnace, that exhaust would be much hotter and it would melt the PVC. But if it is a condensing furnace, the outlet temperature of that exhaust is low enough that it won't melt the PVC. And the nice part about the PVC is that the acid rain in there will not corrode the PVC. So when you see a residential furnace, you'll see a PVC outlet. That means it is a condensing furnace. It is a high efficiency unit. All right, so let's look at this cutaway. All right, so this illustration kind of shows all those different parts of this. Here's the return air. Here's the fan on the bottom. It blows air through the heat exchanger. The space air goes on one side of the heat exchanger and back to the room. The combustion air goes on the other side, and then the junk, see where it says draft hood and exhaust stack, that goes outside. This one is drawn with a metal piece, though. That's the only difference between these two pictures. And it's metal, that means it is a lower efficiency furnace. It's less than 88% efficient. A rooftop unit, here's a better illustration. Think of like a simple, small commercial building where they've got a low-sloped roof. They're going to put a rooftop unit on it. It's essentially the same thing. It's just it's sitting outside, and it's blowing down. That's really the only difference. It has all the same parts: filters, fan, air conditioning system. And we'll talk more about the air conditioning system for rooftop units later. But it also has natural gas going to it, and it has a burner section. Now, this works fine if we have like one big room. In other words, let's say that we have a gymnasium or a small office building where everybody's in cubicles and there's just one big room. A rooftop unit like this works just fine as long as We only have one zone that we're trying to heat and we're trying to cool. But what if it gets more complicated than that? Think like large office buildings. Think like town engineering, or a whole campus like Iowa State. How can we heat each different room to a different level, and how do we do it efficiently? We can't have 100 furnaces on a building like town engineering, which is about what you'd probably need, maybe even more. So if we're going to heat a complicated building, we're probably going to switch to a boiler. Let's talk about boilers. We can either have a steam boiler or we can have a hot water boiler. A hot water boiler doesn't boil anything. Remember this discussion back from Connie 241. Why did we call the thing that heated the DMACC building a boiler even though it didn't boil anything? We call the thing that heats water for heating the building a boiler because we always have. When we were originally doing big buildings, we literally would have a boiler that you scooped coal into, almost like a steam locomotive. They'd dump coal into a coal chute that go down to the basement. They'd shovel that coal into a big cast iron monster. And all that cast iron monster is basically a fire with a big tank above it. And they set enough coal on fire to boil the water, and it go up to steam radiators. Those are reliable. They work for years and years and years. I've got some pictures here in a little bit of some boilers that have worked for 80 years. However, they're dangerous, as I hope you've seen the videos by now. There's some danger associated with them. There's a whole lot of maintenance associated with steam systems. And they take up a lot of space. All right, now, we still see a lot of steam systems, though, in larger buildings. We see steam systems from the video. You see, New York City has a complex all to itself of steam systems, 100 miles of steam pipe. Iowa State heats all of their buildings with steam. They take steam to each building on campus. And the reason to do this is that if you need to transfer a lot of energy and you need to do it over long distances like a college campus, New York City, or maybe even a hospital complex, steam can transfer more energy through a small pipe than any other option that we have. I mean, more so than just heating hot water and pumping that around a campus. All right, but hot water is usually used when we get into a single building, a large building, all right, or even small ones. You might even find a residence with a hot water boiler. And just like the furnace, we can have condensing hot water boilers and non-condensing hot water boilers. All right, let's keep going. Let's talk a little bit about the different types of boilers. Steam is going to be defined by its pressure. A low pressure steam boiler is anywhere from 5 to 15 psi. In other words, the steam itself coming out of that boiler is at 5 psi to 15 psi. A medium pressure boiler is going to be 15 to 45, and anything above 50 is a high pressure boiler. The steam system in New York City operates at about 100 psi. The steam system on this campus on Iowa State University also operates at about 100 psi. They are both high pressure systems and therefore high potential energy and therefore high danger. Hot water. There's two types of hot water boilers. We can have like a cast iron monster in hot water. In other words, high mass, big, lots of steel, not terribly efficient. Or we can have modular boilers, coil boilers. I'm going to refer this to as like a copper fin tube boiler or a condensing boiler. Those will have very little water in them, but they will be very, very efficient. Here, I've got some more pictures of each of those as we go on. All right. Here's just like a picture if you're looking down on the top. This is a non-condensing hot water boiler. Have the fire here in the center. It conducts energy through these heat exchangers, and we have the water on the other side of these that goes through these coils. The energy from the fire goes to heat up the coil, heat up the water that's passing through the coil. Very simply, this is a very simple, like you might find in a residence. We have water, return water coming back to the boiler. It's heated and it comes out. It's going to go around a bunch of individual zones. Like I said, this is a residential sized system. Oh, by the way, don't get too caught up on the piping layouts yet. When we get into the third part of this class, and we're going to get into plumbing, piping, and hydronics and fire protection, we're going to talk a lot more about water flow and pumping later. All right, a condensing hot water boiler. So we're still making hot water. It's just that water coming back from the house has to be much cooler. To get more heat transfer from the fire to the water, we have to have that water as cool as possible. Boiler efficiency is determined by return water temperature. Once again, we're going to have more discussions on this when we get into hydronics, but for right now, I just want you to know that in order to get a hot water boiler to condense, we can't heat that water up a whole lot. It has to be fairly cool, like 130 degrees and below. Here's kind of a cut section of one of these condensing coil type boilers. The part in the center, usually it's a ceramic chamber where we bring in combustion air, combine it with natural gas, and set it on fire. See these U-shaped coils here? That's where the water goes through, where the water passes through to get heated up. Notice as we compare this to a cast iron one, these coils are very small. The tube thicknesses are very thin. Think of it this way. As we look at boilers, condensing boilers and non-condensing boilers, there is a trade-off to be made. The condensing boilers are more efficient. They will take up less space, physical space in a building. And because they are more efficient, we're going to pay a lot less for the energy to heat the building. That's all well and good. The other option, the large cast iron ones, have the advantage of reliability. And here's why. If we look at, let's just take an analogy, car racing, NASCAR. How many races does a racing team get out of an engine in NASCAR? The answer is probably one. Maybe two, but probably one. And why is that? Well, it's because we are pushing that engine right to the ragged edge of failure. Many times in racing, past failure. In other words, it's not a stock car. If you as a consumer had to go buy a new car after every 500 miles, that would get you pretty upset. In other words, you're looking for long-term reliability. You're looking to drive 55 miles an hour or 70 miles an hour, hopefully at most 70, right? But you're not pushing that engine right to the ragged edge of failure for 500 miles. That's what car racing does. In other words, they exchanged, in order to get greater performance, they exchanged longevity and reliability. It's a trade-off. So to get the higher level of performance, we're going to make some trade-offs for reliability. And one of those trade-offs is this, the heat exchanger wall thickness. Remember, our equations for heat transfer across the wall. Now, we were talking about a building wall. Q equals UA delta T. All right. Well, let's think that same equation applies to the coil wall here in a boiler. In other words, if I want to maximize the Q, the heat transfer, I have to look at the other side of the equation, the U value. Well, how do I improve the U value? And in this case, improve means how do I increase the U value, lower the resistance? For a wall in a building, I want increased resistance because I don't want heat transfer. That represents wasted energy. But in a boiler, I want to increase the heat transfer. In other words, I set this natural gas on fire. I want as much energy out of it as possible. Therefore, I want as low an R value for my heat exchanger wall as possible. So how do I maximize efficiency in a boiler? 1, pick materials that are good conductors, like copper, or maybe stainless steel. Maybe I increase the surface area. In other words, I have a lot of these coils in here, right? Maybe I make the wall of those coils as thin as possible. Notice that last one. That increases the heat transfer, but thinner and thinner and thinner coil walls increases the chance of failure. So there's our trade-off. I'm trading off life expectancy for performance. I can get greater heat transfer by making this boiler smaller, making these coils as small as thin as possible, but I am running closer to failure. Think like on one of these, 15, maybe 20 years is a good life expectancy for these high efficiency coil boilers. Here's just we'll just keep going. There's other pictures. All right. We'll talk about water later. Here is the graph that I want you to remember. Boiler operation. So remember that Q equals UA delta T. The U part, that's a function of what do I build the boiler out of. The area, once again, it's a function of how much surface area for the various coils that I have. Delta T in this case is the difference in temperature across the coil. It is the temperature of the fire on one side versus the temperature of the return water on the other. The cooler this return water is, the greater the delta T across the coil and the greater the heat transfer. In other words, if that return water is cooler and cooler and cooler, I will get greater efficiency out of it. Once I get down below about 130 degrees, I'll reach the condensing point, and now I'm going to get water forming in the stack of that boiler. Now, at some point, this water gets too cool to actually heat your space. Once you get, if our space is 72 degrees, I've got to have that water warmer than that to add heat to it. So there's a limit to how cool I can make that system. All right, I'm going to talk about hot water piping, like I said, later. But I do want to talk about steam. All right. And I realize you probably can't see this all that well on my screen, but this is why when you're watching these videos, I really need you to have these slides handy so that you can follow along. The basics of a steam system, small, large, whatever. All right? I've got a big tank of water right here. See the water? Below it, I'm going to set something on fire. I'm going to set natural gas on fire. I'm going to set coal on fire. I'm going to set fuel oil, whatever that is. But I've got a fire below it that transfers the energy from the fire to the water. That water boils. Steam rises to the top and goes out here. See where it has the main steam line? That comes off of the top of the boiler. I want that steam to be pure steam. I don't want there to be any moisture droplets in it. Because once it hits this main header, that steam is going to be moving really, really fast. I don't want any water droplets in that main header because, believe it or not, it's going to be moving fast enough that those water droplets can actually cause damage over time, damage to the inside of the pipes. They can actually wear away the pipes. They can actually scratch the pipes. And once we get a scratch and we get water on it, then we might get corrosion from the inside out. If we have a big slug of water that by accident goes through our steam piping, it can actually hit a pipe hard enough to break it or cause it to rupture. We'll come back to that as we look at the New York City steam pipe accident. We'll kind of discuss that in a little bit. All right, so we have the main steam header. This might go across the building, it might go across the campus, or it might go across the city, like New York City's example. So these main steam headers are going to be pretty big. The whole point is it's going to go somewhere. See this riser, right? Somewhere it's going to get used. It's going to get used to heat a building. It's going to get used to heat outside air. It's going to get used in a hospital to disinfect medical instruments. Who knows where it's going to get used, but we're going to use that steam somewhere, and that steam at some point is going to condense and come back to the boiler. When this steam condenses, in other words, when we've gotten the energy out of it, that water is still hot. There's still energy in it. I want to take that hot condensate and pump it back into the boiler to turn it into steam and go around and around. And why do we do this? Why do we flash it to steam and then let it cool down and condense again? All right. We are taking advantage of the phase change here. We can heat water up or cool it down and put in a certain amount of energy, which is fine. But the change in phase per pound of water is a whole lot more energy than just heating that water up. We're taking advantage of, hopefully you've heard these terms before in physics, latent heat of vaporization. Got a little illustration here that kind of shows this a little bit better. So if we have water at 70 degrees and we add 142 BTU, and this is 1 pound of water, all right? If we add 142 BTUs to 1 pound of water, that'll take it from 70 degrees to 212 degrees. Remember, the amount of energy that it takes to raise 1 pound of water 1 degree Fahrenheit is 1 British thermal unit. I know. SI units are easier to use and understand. Sorry, we're still using English units here. Even if the British don't use their own units, we're using them because that's the industry that you're going into, or at least learning about. So we add 142 BTUs to get it up to 212 degrees. All right. To take it from 212 water to 212 degree steam, we have to add an additional 970 BTUs. Per pound of water, that is a lot more energy that we're putting into the water, which means when we use it in a radiator or in a coil or at a building, and it condenses back, we get that same 970 BTUs out. Per pound of water, that is a lot more heat transfer than merely heating it up and cooling it down. It adds a lot of complexity and it adds a lot of safety issues to it. But if I need to move a lot of energy in a pipe, steam is way more efficient at it than just hot water. Now, look at this, though, down below. All right. If I increase the steam to 100 psi, you have to add an additional 880 BTUs per pound. So going from just atmospheric pressure steam to steam at 100 psi, that almost doubles the energy input. Per pound, that is a lot of energy. But understand that that means the potential energy is there. If you cannot contain this 100 psi, it can result in a catastrophic failure, and hence some of the videos that you took a look at. All right, let's look at a little bit better schematic of steam. All right. We set some fuel on fire. We've got a tank. We turn it into steam. That's the red part. We transmit that to whatever, right? Whatever we're using it for, like a coil or a radiator or whatever that is. So notice the steam comes off the top, and each one of these taps comes off the top. We're trying to make sure that we get pure steam and no liquid vapor. Because if there's liquid in here, now that can damage the pipes. Notice these traps along the way, like at the end and along the way. As we take steam and transmit it a long distance, like at Iowa State, from the boiler plant all the way here to Town Engineering, that's a lot of piping surface area. No matter how well you insulate that pipe, you're still going to have heat loss. In other words, it is still going to lose some energy along the way. We can't ever get that heat loss to zero, but what we can do is minimize it, and that's why we insulate it. But we're still going to lose energy. Along the way, some of that steam might condense, and we have to get it out of there, and that's what these traps are for along the way and at the end. And also, at everywhere where we use steam, there's a trap. In other words, once I get that energy out, whether it's by accident in the pipe or on purpose at a coil, it's going to lose energy and condense back. We're going to drain that back. Notice that this is gravity drained to a tank, and then we're going to pump it into the boiler because there is still a whole lot of energy in that condensate. This condensate is going to be just below, just below 212 degrees, right? It's probably 180 degrees and hotter. All right. Well, let's skip some of these, right? Steam traps. I'll let you just look through these. The important part that I wanted to get. Here we go. Let's look at some examples, some pictures. This first one is a new steam boiler. Cleaver Brooks. 7 million BTU per hour. 7 million is a bunch. All right. Think like probably not enough to heat all of Town Engineering, but heat a very, very large building. Notice the dimensions on this thing. 18 feet long, 6 feet wide, 8 feet high. This is massive. The part of the reason that it's massive is this tank has a whole bunch of water in it and steam at the top of it. In other words, it needs a very, very large volume to make this work. Here's another, this is just a picture of one I found. And this is in a hospital in Illinois. Just once again, this is a Burnham boiler. Or no, I'm sorry. This is a Burnham boiler. This is a Burnham boiler, just looking at it from the end. This is a high efficiency coil boiler. Each of these, this happens to be a Thermal Solutions one. I typically design boiler systems around this one. This is my go-to. Thermal Solutions. Each of these, this is like a 3-foot square box, probably 8 foot high. Each of these could do 2 million BTU per hour. Now, just check this out. Here, this one is actually a hot water boiler as well. Old, cast iron, big, very reliable, big in size. It would only take, let me think here, 3 of these to replace something big like this or big like this. Notice the advantage of these things. Let's say one of them does fail. They can fit through a standard door width in a mechanical room. Probably one sheet or one plumber with an appliance cart can get that through a door. more easily replaced because they are physically smaller. However, because they have a lower life expectancy, they better be more easily replaced. The smart way to design around these high efficiency boilers is to have multiples of them so that you can do maintenance on them regularly and so that they can be replaced frequently, so that when one does fail, it's not a catastrophe. Let's look at some pictures of some older cast iron monsters. Here's a picture of, these are Kewaunee boilers as well. Notice these openings. These are holdovers from when we scooped coal into this. They've probably replaced this with either fuel oil or natural gas. Here's a picture of one still working. A student sent me this picture. His dad is a superintendent for an apartment building in Chicago, and they still have an 80-year-old Kewaunee like this. Here, see this pipe? They have converted it from coal to fuel oil and from fuel oil to natural gas, still using the same boiler. And the reason they can do this is that the interior of this boiler is simplicity itself. There is a pit that we throw fuel in and we set it on fire. It is no more complicated than that. That's why you could shovel coal in it, or you could just dump fuel oil in it, or just blow natural gas into it. It doesn't matter. It all burns in the combustion chamber. It's reliable, and you'll see why here in a second. Here's a picture of the inside of the combustion chamber. Once again, this would be better if you look at this, download the slides and look at this on your own computer. This is brick. These are fire bricks. In other words, they build a big brick base at the bottom of this boiler and set the boiler on. This is just simply a pit that they throw the fuel in and set it on fire. Next picture. This is the air control system where now they inject natural gas through these nozzles. This is where they blow natural gas in and set it on fire. There's another picture of the natural gas nozzles. Now, see the bricks? So the fire is right here. The fire goes through these tubes and makes a loop through the boiler, the water section. So this is the fire side of the tubes. Look at a little close up here in the corner. You'll notice one of these tubes was leaking. Notice there's a big pile of rust here. One of these tubes was probably leaking for most of the winter. You're supposed to do an inspection on these yearly, right? And you're like, yearly? Wait, how does this work? Well, they probably just, once they notice this leak, and there's a leak here too, they just fix them. Just re-weld it and fix the tube. You're like, wait, that's a big pile of rust. So, here's the point. This is why they are reliable. It can rust, it can fail, and it still keeps on working. And that's why this thing has lasted 80 years, is that, all right, part of it broke, it kept on working. During the summer, we drain it down, find all the leaks, fix them, it's ready for next year. Now let's go to the other side of this. This is the water side. All right, like looking at the top of it, this is the water side where the fire will heat the water. All right, let's go to. Got a couple of. I want to talk about the videos that I had you look at. All right. Well, first, let's look at this. Look at this NBC article. There was a catastrophic steam pipe failure in 2007 in New York City. All right, and when I say catastrophic, here's the hole that it left in the street. See, this is a tow truck that accidentally drove into the hole, and it killed one or maybe two people from that accident. It killed one or two and burnt several others very, very tragically. When they had to fix this part of the street, they had to close this whole intersection, excavate about halfway down the block in all 4 directions, and rebuild all the infrastructure. It completely blew apart the entire intersection, and the hole was big enough for this tow truck to drive into. Let's go back to that article. You can see that same tow truck from a different angle right here. All right. I will let you read through it. It's a really good article. Please take some time. Here is the picture that I really want to get to over here. So buried below the street are these steam pipes. The one that blew up, I want to say, was either 20 or 24 inch steam main at 100 psi. All right, so buried down somewhere between 4 and 15 feet below the sidewalk and below the street are these steam mains. See that little orange cone? That's where the steam vents, excess steam that accidentally gets out, is going to be vented that way up above the windshield height of cars, so it doesn't obscure people's vision. All right. Now, periodically there'll be valves so that the workers can isolate different sections. Now, understand the potential energy in this. All right, here is some video live or taken live by just a bystander, and they are a block away at least, probably further. And I want you to watch this video just because listening through it through this microphone won't give it justice. This was so loud. People thought, this was after 9/11, obviously. People thought it was another building coming down. That's how loud it is. I absolutely believe them when they say it sounded like a building coming down. The potential energy in 100 psi steam is absolutely massive. And if you look at the pictures of the aftermath, and I'll let you look those up. They're pretty interesting, but they don't really show anything new. My point is that it ripped apart a concrete street. Just think about the potential energy there. Also, just keep in mind that it is the same pressure, or really close to the same pressure, as the steam lines on Iowa State campus. So as you're walking along campus in the summer, or rather I should say in the winter, you'll notice some areas that don't have snow. Those are above steam lines. That's all the energy that is lost through the walls of the pipe, and there's steam tunnels that go below Iowa State, and those tunnels are hot because of the steam lines going through them. If there was a catastrophic failure like the New York one, the same thing could happen at Iowa State. But let's talk about exactly what caused that to happen, or at least my theory on it. Okay, so go back to the PowerPoint slides and go back a ways to this diagram. All right. So see these steam traps? They are designed to remove a certain amount of condensate. If they are overloaded, in other words, let's say that we have more heat loss through that pipe wall than we expected, or let's say maybe, and in a long run of this, these steam traps would be located, there'd be several of them located periodically to drain the water out of the pipe. Let's say that they were overloaded for some reason. You might get a little bit of water in the bottom of this pipe. Let's talk about that for just a second. If we've got water in the bottom of this pipe and hot, fresh steam running over the top of it, what is going to happen right there? I've got water, I've got steam. The steam obviously has more potential energy than the water. They're going to exchange energy. That steam is going to try to heat up the water is going to try to cool down the steam. I'm going to get steam condense, but I'm also, as fresh steam comes over it, I'm also going to get steam or water flashing to steam. Well, what happens to the specific volume as you go from water to steam? It expands greatly. And what will happen is the pressure in this pipe will actually surge, almost like a steam engine. Steam engines do this. They puff, they surge, they build up pressure and use it, and build up pressure and use it. Well, if that same thing happens in this pipe, it will cause pressure spikes. There's a steam, one of the companies that sells steam equipment, they have what they call their steam trainer, where you can go and get training on such things for engineers and contractors to learn how to design it and install it. They had a system that simulated this exact failure, where you have steam and you have cool water on the bottom of that pipe. And they actually do this trainer. They get it to start what I would just call kind of puffing or chugging away. And those spikes in pressure, it was 1 psi steam, and those pressure spikes got up to 12 psi, and then they had kind of a safety blowout at the end of the pipe to relieve that pressure. So a 1 pound, 1 psi steam system can cause pressure spikes of 12 psi. Let's go to New York City. Let's say that this is 100 psi steam, like Iowa State or New York City. That means these pressure spikes could easily be 1200 psi. Let's also say in New York City, maybe some of these pipes are 50, 60, 70 years old or older. It isn't unreasonable to think that a pressure spike could cause a catastrophic failure of that steam system and cause it to rupture. And I think that's what happened. Moral of the story, most of you will never work on steam systems. However, many of you may end up being general contractors that have subcontractors working on steam systems. Here are some things that I want you to understand. 1, steam systems are dangerous, and when they are neglected, they can kill people. 2, when you're doing maintenance on a system like this, use caution. If all of a sudden, let's say that an owner wanted you to replace the insulation on this long run of steam pipe, your subcontractor might say, it'd be cheapest if we're replacing the insulation from the boiler plant all the way to town engineering. The easy way for us to do this is to get down that steam tunnel and remove all of the insulation, and then come back in and replace all the insulation at once. That might be the efficient and easy way to do it. However, you've also, by removing all that insulation at once for, 2 miles? Maybe almost, let's call it 2 miles between the steam plant and town engineering, you've also increased the amount of heat transfer, and you've increased the amount of condensate that's going to be generated until you get that new insulation on. What I want you to recognize is that removing insulation off of a steam pipe is also a potential risk, and that your subcontractors, you need to make sure that you're working with subcontractors that understand that and understand the dangers, because if something goes wrong, it will be catastrophic when you're dealing with steam systems. All right, the last thing I wanted to look at here is, and I hope you watch this, the Mythbusters. I put 2 of them on here. I'm going to explain one of them. Hope you watched it already. A couple things to know about this particular experiment that they did, and it's a really cool experiment. I don't want you to think, though, that this could happen to a normal water heater, a normal domestic water heater. They did a couple of things to cause this particular explosion. One, all water heaters have a safety pressure relief valve. They will have 2 of them. What they did is they took off those relief valves and capped them so that the pressure couldn't be relieved through a mechanical device. So that's not natural. Also, they're going to have an electronic safety on these, where If the pressure gets too high, it's going to shut off or the temperature gets too high, it's going to shut off the electricity to it. So they disabled that as well. Now, those are things that could happen in the real world. All right, I don't want you to think that couldn't happen, but they went to some special lengths to make sure that it did happen. That particular water heater got up to about 330 psi, so it's very high. The impressive part there is that it held to 300 plus psi. That's pretty amazing. All right, but then when it failed, and this is kind of the nature of steam failures, when it failed all at once, catastrophically. In other words, the bottom busted out, and then the rest of it being a cylinder. The circular part was the strong part. The base was the weak part, the joint where a flat piece went to the cone or a cylinder. That's the weak part. It failed. The rest of it stayed intact. All that energy was pushed down, and it launches this in the air. And it went up, if I remember right from the video, I think it went up a couple hundred feet. And they've got some awesome slow motion stuff here. Watch this one, and also watch the one, I put 2 Mythbusters. They're different videos. They did this on this one little building. They also did it underneath a 2-story structure and launched it through the 2-story structure, which is totally cool. And here's the slow motion. See that steam come out of there? And here's the cylinder of the water heater shooting up. Oh, one last thing that they did to make this happen. They only filled the water heater up halfway in that cylinder. When they filled it up solid with water, it wasn't a very interesting failure. But they tried it again and only filled it up halfway. That gave a large volume for that steam to expand into. And that was what was necessary to get that particular type of a rocket launch. And by and large, really cool video. All right, so definitely watch those videos if you haven't. Take the time to listen to their discussion, but also you need to know a little bit of the background to understand, get a little bit of perspective. All right, so I realized that this video, we had 2 days on this subject, heating systems. So I'll give you some time to do that before I post my next one, maybe Monday or Tuesday. Actually, I might just do all of the refrigeration cycle at once. I might post it on Thursday. All right, so stand by for more information. And remember, boilers and the refrigeration cycle are on exam 2, so they're not part of exam 1. All right, until next time then.